Hi, my name is Jennifer Jamison. I'm a 5th-year student in the Department of Chemistry. And I've been working in Dr. Matthews' lab in biochemistry and cell biology for the past 2 years. What I do is I study nanobioconjugates. Basically, nanobioconjugates are nanomaterials that have some sort of biomolecule attached to them. This biomolecule can be DNA, RNA, proteins, peptides, any sort of biomolecule. The reason why we study these particular materials is because they have dual properties. So you have a biological molecule, but you also have a nanomaterial, and you can combine both of their properties. So for a biomolecule, maybe it can specifically recognize breast cancer, and a nanomaterial, it can light up. So if you put those together, you can get a breast cancer detection agent that will light up in the presence of the cancerous cell. So basically, one of the ways that we test if we have sufficiently attached the protein to the nanomaterial is we do what we call a sodium chloride flocculation assay. We take a constant concentration of our nanoparticle and we titrate an increasing concentration of protein, and then we let that sit and we add in a small volume of 10% sodium chloride. And what that does is it breaks up the charge on the surface of the nanomaterials. So the nanoparticle, in this case, it has a negative charge. And since sodium chloride is a strong electrolyte, the sodium chloride will dissociate into sodium plus and Cl minus ions. And the positive parts will associate with the gold nanomaterial and minimize the negative repulsive charges between them. And when that happens, they turn purple. So as you can see in this particular case, they turn purple because there's nothing on the surface. So what you would see in a real assay is it'll go from purple all the way to red. And then the red part, the first place where it goes from purple to red, that's the place where you have saturation. Basically, once we determine the ideal range of saturation, then I take each of these conditions and I scale them up to 500 microliter volumes, and then I run them on a gel, a polyacrylamide gel, to quantify the amount of protein that I have. And the darker the spots are on the gel, that corresponds to increased concentration of protein. To run a gel, of course, you have to apply a voltage, so you have to put it in this apparatus so that you can apply the charge and cause the protein to separate out. This comb helps me to make lanes in the gel, and when I take it out, I can't see them, so I use this to tell me where they are, so I don't poke a hole where I don't want to poke a hole. In this particular case, we line it up with the comb, and then we pull the comb out with a constant force. So here it goes. So there it is, done. This contains a dye, and basically we would add this to each of our protein solutions. So this is what we call sample buffer. And this has the sodium dodecyl sulfate in there that causes the proteins to be charged and linearized. So you can see it's dark blue, and that's why we dye it blue, so that you can actually see that you have in fact loaded the protein on the gel. And so to actually finish this up, you would load all your wells, and then we just set this over this, and we plug it into this apparatus, which will apply the voltage and current that we need to separate out the proteins. So the gel is run. All of this would be down here somewhere in the gel, and then this, it just picks up. See how it kind of moves? It's wiggly. It's like jelly. Then you can stain this using these solutions. The proteins would be in the gel, and it would get really, really dark. And then you would destain it, and then you can dry it and scan it into your computer. So when it's considered hot or radioactive, we dry it in the gel room back there, and then we scan it in over there. But yeah, don't go in that room, that's the hot room. Whatever you're working on, it could be a variety of different things. It always has an application to the real world, and so I really like the fact that when I'm in the lab, not only am I just doing what I'm doing, it could potentially impact the way we're living in the world today. I actually want to be a professor and show people that a scientist is not one particular type of person, that it could be anybody who is motivated and willing to work hard. I'm like really lively, and so they can't believe that, wow, you like to shop, you like to do this, you're playful, and you're going to be a scientist.